All right, so can you guys see my screen now?
Yes, sir.
Yes, sir.
All right, good. All right, so I have already saw the your scores in midterm exam in your exam. So I was quite disappointed because there were only three who were able to pass the midterm exam. So the highest is 70 out of 100, and then the other two is 60 out of 100, and then the rest, some are 55, 50. But as we all know, that is not the passing score of of UC. So you need at least 60% to get the 50% rating or the passing score for that specific activity. And I I saw that in superposition theorem, none of you were able to get it. As you guys can see, this is the statistic of your midterm exam. So 0% answered correctly. All right. And for the remaining superposition method, so there were others who got one correct answer, one respondent. So that's 4%. And for the nodal method, so there were only 13% for this specific question and 8% for this question. And then, yeah, so you guys got quite very low when it comes to the last topic, last two topics, the superposition and then the nodal method. Maybe because I wasn't able to give a quiz. So maybe that's the reason why. Well, you don't have that much time before. That is why I wasn't able to give a quiz for those two remaining topics anymore. So what I would like you guys to do is I'll create another like activity for this one, superposition method. Same variables, same unknowns, okay, same values, and same everything. Okay, so I'll give you guys 1 week, okay, to redo those two topics, okay, and then I will add what those scores that whatever you will get, okay, to your midterm score, okay, since the scores are really low, so some even get a zero, some get 10, 20, 15. So yeah, so that's what I would like you guys to do for now. Okay, so are we clear with that one?
Yes, sir. Thank you po.
Okay, so additional points lang siya. So if you will not get anything, then I am really so sorry. This is like your one only chance to cope up and then to make your midterm score at least uh, placing at least let's say 50 out of 100. Well, I think that's already good. But if you will only get 20, then I think that is not a very good start, because your midterm grade will, be part of your final score. So that's the reason why it's much more better if you have a higher grade in midterm and then have a lower grade in finals. Because if you have a lower score in midterm, then 50% of that will be carried to your final score, in which, of course, you will have a hard time in catching up. All right, so I haven't created this one yet. So I'll just put it right here, like additional points for uh, midterm. Okay, so I'll upload that one later on. But for now, we have to finish these two topics, module 7 and 8, because maybe next meeting is coming Thursday, June 3, we might not be able to meet again, okay, due to the webinar that I'll be attending. So I'm not really sure if we will meet this coming Thursdays. That is why we have to finish the module 7 and 8 right now. So don't you guys worry. Module 7 and 8 are super similar with each other. Okay, and then they are super easy to understand. Okay, all right. So before we proceed with our discussion for today, do you guys have a question or clarification so far? Also one more thing. I haven't checked your midterm exam yet, since there are still others who haven't taken the midterm exam. So I want them to finish their midterm exam first before checking everything. Okay, so there might be some changes. So you might get a higher score depending on your solution, depending on your final answer. If it's super close with the final answer, like for example, it's the answer is 14.2 and then the margin error is 1. So 13.2 up to 16.2 is acceptable. But if your score is, let's say, 13.1, okay, which is super close with 13.2 already, so I might, you know, give you the additional points, maybe half of the points of that one. So instead of 10 points, maybe I'll give you 5 points. So yeah, well, uh, that also depends on your solution, if you have the correct solution or not. Okay, not just the final answer. All right. So any questions so far or clarification before we will start with the module 7?
None, sir.
All right. Sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there were only 10 out of 24. So that's always the case. Always half of my students are not present. Anyway, so you guys already know, of course, we're going to have a quiz, but I don't know when I will publish this one, so not sure yet. Maybe after this, uh, yeah, after our discussion. So maybe I will set a deadline for this one, so you can start as soon as possible to finish the Thevenin's and Norton's theorem quiz. So that next week, uh, we'll now move on with these four modules actually. So module 9, 10, 11, and 12. Okay. So yeah, anyway, let's now start with the Thevenin's theorem. All right. So for the Thevenin's theorem, this one is super similar with the superposition theorem, the nodal method. Okay, so as you guys can see, it also needs transformation. So this one is possible to simplify any linear circuit, no matter how complex it is. Okay, so yeah, I guess this is super possible in any kind of circuit. Okay, unlike the Maxwell and then the Kirchhoff's, we have limitations for some circuit. But for Thevenin's theorem and then Norton's theorem, they are much more dynamic, flexible, and uh, easier, I guess. Well, depending on your preference, there are things that much more easier to solve when it comes to Kirchhoff's, Maxwell, superposition. So they have their own edge with each other. All right. So take note that this one is only possible to simplify to any linear circuit. Okay. So what are linear circuits? So I'm say linear, there should be no exponents or roots in that circuit. Okay. And if it only contains components like resistors, inductors, and capacitors. And then that is much yeah, more likely they are non-linear already. Okay. So like for example, there's one components like we have gas discharge and semiconductor components. Those are already non-linear components. Okay, but don't you guys worry. We will not be discussing about the inductors and capacitors in this subject. Okay, because inductors and capacitors is mostly introduced and discussed in electronics. Okay, so this one is electrical circuits, and then the other one is fundamentals of electronics. Okay, that is where we discuss inductors and capacitors. All right, so yeah, simplification. So let's use this example. So as you guys may have already noticed, this one is the same circuit diagram, the same variable, same values, okay, like what we have in I guess it's in Kirchhoff's, in Maxwell, and in superposition. Okay, so we'll try to prove that their values are the same with each other, even though we've used different method. Okay, so this is the one that we're going to use, and then this is the one that we're going to transform into a Thevenin's equivalent circuit. All right. So in order for you to get the Thevenin equivalent circuit, okay, we have 4 steps for that. So the first one, okay, is remove the RL. Okay. RL is the load resistance, like in here, you can just simply remove it, or short circuit, not short circuit, open circuit RL. Okay, that's the very first step. Second one is find the RTH. Okay, RTH or VTH, oh, any of those two, as long as you'll be able to solve those two unknowns. Okay, RTH is the equivalent resistance in terms of the Thevenin equivalent circuit, and then VTH is the uh, voltage Thevenins, or the equivalent voltage of the Thevenin equivalent circuit. Okay, so as long as you have those two already, and you may now proceed to the next one, wherein you can now transform it. Transform. My bad. Okay. Well, yeah, that's right. RTH and then VTH, and then you can now transform that one into Thevenin equivalent. Then from here, you can now find the unknowns that you were looking for. Let's say the total voltage across the entire circuit, the total current, the voltage drop across those resistors, the current that is passing through those resistors, okay, etc., etc. Solving for unknowns. Right, so those are the only steps that uh, you can apply to solve for the unknowns with this circuit. All right, so without a further delay, let's try to apply those rules or steps. So again, the first one is we have to, okay, let me just get this one. Okay, let's get this original circuit. Okay, one thing that you may also notice is that it jumped right away to this Thevenin equivalent circuit. Okay, and then more explanations on how to get that one. Okay, you can actually apply any uh, rule that you know. Okay, you can apply Maxwell, you can apply Kirchhoff's, you can apply superposition, you can apply any method that just to get the RTH, the VTH, and the others. Okay, so in here, okay, the first thing that we need to do is apply this one. So remove RL by replacing that one into open circuit. Okay, or let me just put this one right here so that we know that the value of your RL is 2 ohms. Okay, the second step is look for VTH or RTH. But in my case, I always go for RTH. Okay, this is always the one that I try to solve first when it comes to Thevenin's theorem. But you can also find the VTH if you want. Okay, so in here, in order for us to find the VTH, okay, we have to short circuit or open circuit your voltage sources. Okay, so all sources will be removed. This is super ugly. Let me just use this one. All sources be removed. So how do we do that one? For the voltage sources, okay, just short it. Okay, short circuit. Apply short circuit. For the current sources, just open circuit or leave it open. Okay, So if it's a voltage source, then short it. If it's a current, then open that one. Okay, leave it open. All right. So in here, as you guys can see, we only have voltage sources. So all we need to do is remove that one and then short those two voltage sources. So I'll just remove this one and then place it right here so that we know that the value that's that one is 28. The same with this one, and then place it right here so that we know that the value of B2 is 7 volts. So in here, I'll just simply short this one. Okay, there you go. Same with this one. Okay. And then from here, you can now find the RTH. So if you're going to take a look on this one, you might think that this one is in series connection, but they are not. Okay. So as you guys can see, we didn't fully open this one because this one will serve as your node A and node B. This is your node A and then this is your node B. Okay. And then how do we solve? How do we solve for the RTH? So just by simply forming this one into a parallel connection. So as you guys can see, if you're going to form this one into this kind of circuit, okay, we have this node A right here, and then this is the R1, and then we have this node B right here, and then this is the R2. Okay, R1 and then R3, my bad, not R2, because the R2 is the load resistance. So in here, in order for you to combine them, you have to apply the parallel rule, okay, because they are in parallel with each other. So for the RTH, so the formula for that one is R1 times R3 divided by R1 plus R3, okay, wherein R1 is 4 ohms, and then R3 is 1 ohm, and then R1 is 1 ohm, 4 ohm, and then R3 is 1 ohm. So 4 times 1 is 4, and then 4 plus 1 is 5. So 4 over 5. And in calculator, so 4 divided by 5 is 0.8. Um, okay, so that's how to solve uh, the RTH for the Thevenin's circuit. So were you guys able to follow so far? Yes, Miss Kate?
Yes, listen lang.
All right. So how will you know where to find the RTH? Okay. So wherever is your RL, okay, wherever is your RL, and then you leave it open just like that, that is where you can find the RTH. Okay. So this one will serve as your RTH, and then at the same time, later on, this is where you are going to solve the VTH. Okay. So take note, wherever is the RL or the load resistance, that is where you can find the RTH and then the VTH. Okay. So if the RL is on this right side right here, then they are now in series connection. 4 plus 1 ohm is 5 ohm. And then whatever is the resistance that will flow RL right here is now your RTH. But since the node is in right here, node A and B right here, so they are in a parallel connection, just like this one. If you're going to transform that one into something like this, okay? So yeah, that's already it for the RTH. And then for the VTH, okay? So in here, you can actually apply superposition theorem, okay? Like what we did a while ago, like dealing for the one voltage right here and then dealing with another voltage right here and then combine them, having the superimposed values. But that one will, give you a super long solution. So that is why I think it's better to use Kirchhoff's or Maxwell in here, but Kirchhoff's is already enough, okay? So in order for you to find the VTH, you have to apply KVL. All right. So in here, let me get the original circuit. Oh, not that one. That's the Thevenin's. There you go. And then I'll just remove this one again. So in here, we can actually apply KVL. So I will assume that the final or the correct flow of current is clockwise, knowing that this one is larger than this one. So well, logically, this will dominate this voltage source right here.
Ah,
So in here, let's say we have loop 1. Okay? Are you okay, Miss Ubasa?
oh, dahil ano eh, naglablabara kami ni Day.
Are you sick right now, Miss Kate Alexa Ubasa? Alright. Okay, maybe na-open niya lang yung microphone niya. Anyway, so in here we can apply KVL to find the total current first before we can find the individual voltage across this R1 and R3. Okay, so with that, after knowing the potential voltage up to this point and then up to this point, then we can now combine their voltages in here. So again, like what I've mentioned a while ago, this is where you can solve the value of VTH, okay, on the node A and node B, okay, or node AB. All right, so in here we have positive 28. So if I will label this one, we have positive right here, negative, positive, negative, positive, negative, positive, negative, and yeah. Okay, so this is where I assume my current. So as you guys can see, this one now is still positive, negative, and then this one is positive and negative, considering their symbols of this voltage source. So in here we have positive 28, okay, starting from B1, positive 28 minus I times 4 or times R1. So I'll just put here 4 instead of R1 to have a shorter solution. Okay, that's okay, Miss Aki. Alright, so where is my cursor? And also in here, as you guys can see, I've only used I because whatever is the current that is flowing on this side is the same on this side. Okay, so no need to label I1 and then I2. Okay, because they are just the same. Okay, so the next one right here is minus, okay, another voltage drop for the 28 volts. So minus I times 1, okay, and then minus 7 volts. Then going back right here will be equated to 0, okay. And then from here, you can now combine similar terms. So 28 minus 7 will give us 21. And then in here, you can combine those two current. So negative 4 plus negative 1 is negative 5. So negative I times 5, okay, is equal to 0. And then from here, you can now solve for the I. So you can transpose this one on the other side first. 21 is equal to I5. So this is I, not 1. And then from here, you can now get the value of I. So I is equal to 21 divided by 5. So in calculator, this is 4 point something. So this is 4.2. Okay, 4.2 amps. Okay, this is now our total current in this entire circuit. Okay, so after getting the total current, then we can now solve for the voltage drop across R1 and then the voltage drop across R3. Okay, so let me just zoom out. There you go. So I hope you guys can still see the values clearly. So in here, in order for you to get the potential voltage across AB or the VTH, okay, you have to get the individual voltages across R1 and then R3 first. Okay, so in that, you'll be able to know what is the final voltage that is flowing from here to there, and then what is the final voltage that is flowing from here to there. Okay, just by combining them. All right, so in here for the R1, so as we all know, VR1 is equal to I1 or I times R1. Okay, wherein I is 4.2 and then R1 is 4 ohms. Okay, so VR1 is equal to 16.8 16.8 volts. Okay, and then for the VR2, we have I times R3. So in here, I is 4.2, and then this one is R3. R3 is 1 ohm. So 4.2 times 1 is still 4.2 volts. Okay, there you go. And then from here, we can now actually get the potential voltage of this one right here for the right side, and then the potential voltage right here for the left side. So how do we get that one? So again, potential voltage on the, let's say, left side for now. Left side. Okay. So in order for us to get the VAB, let's say VAB1, which is on the left side, okay, we need to get the total voltage on the left side, which is 28, minus the voltage drop across R1, which is 16.8, minus 16.8. Okay, so 28 minus 16.8 is 11.2. Okay, so there you go. This is now the potential voltage that is flowing from your left side, okay, which is 11.2 volts. Okay, and one more thing that I forgot to mention is actually you can just solve for one side. Okay, so you don't need to get the VR2 if you already have the VR1. But just to be sure, okay, uh, to make sure that your answer on the left side is the same with your right side, just solve that one also. Okay, so on the right side, so my bad, this is actually already our VDH. Okay, so just one side is enough. Okay, no need to combine those two. So that's the mistake that I have mentioned. So in here, this 11.2 volts is already our VTH. Okay, but in order for us to verify whether that value of VTH is correct or no, we can also solve for the right side. So let's name this one VAB3. Okay, since we have R3 in here. So the same process, we have the 7 volts right here, minus, not minus, okay, because we have this symbol right here. So as you guys can see, this is not a voltage drop anymore. So this is additional, okay, voltage, because we are following this flow of current from this right side, but the original flow of current is from here to there. Okay, so if we are going to consider the outer side, we'll get the same answer, but we have to consider this sign right here, negative and then negative right here. So it will give us negative 11.2 volts. All right, so in here we have positive 7 since we are considering this loop right here. And then positive, okay, so the voltage drop across R3 is 4.2. So 7 plus 4.2 will give us 11.2 volts, which is the same with your left side circuit. Okay, so again, this is already our VTH. Okay, so were you guys able to follow so far up to this point?
Yes, sir.
How about the others? Okay,
Yes, sir.
so again, wherever is our RL, that is where we can solve for the RTH, which we did a while ago for this one, R1 and R3. The same with the VTH. Okay, as you guys can see, this is where we are solving the final value of our VTH. Okay, so looking for the potential voltage on the left side will give us 11.2, and then the potential voltage on the right side, which also give us the same value, which is 11.2 volts. Okay, so from here, once we're done with RTH and then VTH, then we can now perform or get the or transform this one into its equivalent circuit, which is the same with this one. Okay, we have here the E Thevenin, and then the R Thevenin, and then the R loop. Okay, so in my case, I'll just copy. All right, so maybe I'll just copy this one and then remove the other values. So I'll put it right here. So this is our Thevenin equivalent circuit. So E Thevenin is 11.2 volt, and R Thevenin is 0.8, and then our R loop. So from here, we can now solve for the, what can we solve right here? Yeah, we can now solve for the final total current, also the final total resistance, and our final total voltage is already this one, which is 11.2 volts. Okay, so from here, we can now solve for the R total. Okay, so as you guys can see, they are in series, so 0.8 plus, okay, 2 ohms will give us 2.8 ohms. This is now our R total. And then for the I total, so yeah, I total is equal to VT divided by RT. So VT is 11.2, and then RT is 0.8. Ah, no. RT is 2.8. That is the combined uh, resistance. So 11.2 divided by 2.8